Okay, for this section we focus on arithmetic, geometric sequences, arithmetic and geometric progressions, and also arithmetic and geometric series. So what are these sequences, the arithmetic and geometric sequences? There are significant tools, and these tools are a part of mathematical analysis, which we use mathematical analysis to solve basically every mathematical and physical problem. Well, it is originated by the Greeks and the Babylonians, where they were the first pioneers, and they employed these methods, the arithmetic and geometric sequences, to solve pure mathematical and practical problems. So these two are the greatest mathematicians of all time. The Archimedes, he was a Greek mathematician. He is considered to be one of the best mathematicians of all time, out of the antiquity. Personally, I believe he is the best mathematician of all time, because this guy, he basically put the fundamentals, and then others later in the 19th and 20th century, very late on, established a rigorous treatment of what Archimedes had in his works. So he didn't have any kind of competition. He was unique of his kind. The second biggest mathematician of all time is Leonhard Euler, and he used a series to solve the so-called Basel problem, which was one of the most difficult problems that baffled other mathematicians during the 16th, 17th century, and he was able to solve it using the series approach. What are the practical applications? We can apply these tools in cryptography, number theory, telecommunications, game theory, cybersecurity. All these fields use patterns of numbers, and they use these tools to create new keys for cryptography, or to study further how the real numbers behave, or in telecommunications, when we have signals, what sequences of signals we have there. Game theory, and cybersecurity. There are also some patterns with numbers, and we're trying to find different kinds of numbers, like distribution of primes and so on. So these are very important tools, very important parts of mathematical analysis. We start first with the arithmetic progression. Okay, we have A1, A2, A3, etc. We have these terms of the sequence, first term, second term, third term. So the arithmetic progression assumes that the distance between terms is fixed. A2 minus A1 is fixed D. A3 minus A2 is D. A4 minus A3 is equal to D. So from here we can say that A2 equals D plus A1. From here A3 equals D plus A2. But we see here that A2 is D plus A1, so it's D plus A1 to D plus A1. A4 equals D plus A3, so it's D plus 2D plus A1 equals 3D plus A1. And if we want the nth term, equals, if we want the kth term, we can write it as k minus 1 times D plus the first term of the sequence. That's my general formula. So let's have a look at an example. We have this arithmetic progression: 1, 11, 21, 31, 41, etc. The first term is 1, the second term is 11. So what is the distance The distance is 11 minus 1 equals 10. So if we want to find the kth term, we write ak equals k minus 1 times d, which is 10, plus the first term. If we want to find the 20th term of the progression, we put k equals 20, and we have 20 take away 1 times 10 at 9. So that is 19 times 10 plus 1, 191. The 20th term is 121. This is an example here. Now let's have a look at the geometric progression. The first term is a times r to 0, r to the power of 1, a times r squared, etc. The initial value equals a. R is the common ratio. R is the common ratio. So if we want to write the kth term of the geometric progression is a times r k minus 1. You see, if we put k equals 1, you have a, which is the first term, s2, the second term of the sequence, s3, the third term of the sequence. Now let's have a look at an example. We have 1 over 4, 1 over 8, 1 over 16, 1 over 32. So the initial value here, S1, is 1 over 4, and the common ratio, we take the ratio of the two terms, 1 over 8 over 1 over 4. That's 1 over 8 times 4, that's a half. So the kth term should be a times r to the power of k minus 1. So the a is the initial value, 1 over 4 times a half to the power of k minus 1. If we want to calculate the 10th term, we plug in k equals 10, and we have 4, 1 over 4, 1 over 2, and then here we have 10 take away 1. So it's a quarter times a half to the power of 9. Here we can write it 1 over 2 squared times 1 over 2 to the power of 9, and that's 2 to the power of minus 11. So the 10th term is 2 to the power of minus 11. Now let's have a look of these arithmetic sequences. So let's say S1 equals the sum from j equals 1 to n of j, 1 plus 2 plus 3 plus n. This is n times n plus 1. So if I want, for example, to calculate the sum from 1 to 100, is 1 plus 2 plus 3 plus 100 equals 100 times 101 divided by 2. That's 50 times 101, so it's 5050. If I want to calculate, now let's say S2 equals from J1 to n j squared, so 1 squared plus 2 squared plus n squared, this is n plus 1 to n plus 1 divided by 6. So for example, if I want to calculate this sum here, is 1 squared plus 2 squared plus 3 squared 1 plus 4 plus 9. This gives me 14. Now let's check this formula. This can be written as 3 plus 1, 2 times 3 plus 1 over 6. 3 times 4, this is 6 at 1, 7 over 6. That's 12 times 7 over 6. We can simplify this, and this gives me 14. These are called arithmetic. These are two basic arithmetic sequences. Arithmetic series, sorry. Arithmetic series. Now let's have a look when we have geometric series. When we have the sum of all the geometric terms of the sequence from k equals 0 to infinity, a times r to the power of k. So we have a plus ar plus ar squared, etc. This is a times the sum from k equals 0 to infinity, r to the power of k, and this is a times 1 over 1 minus r, and r should be, in modulus, should be less than 1. So let's have a look at an example. The series from k equals 0 to infinity, 2/3 to the power of k is 1 over 1 minus 2 over 3. So this is my r here, 1 over 1 minus r. I can simplify, I can multiply times 3 the numerator denominator, so it's 3 over 3 minus 1 is 3 over 2 over there. Now let's say we have a double geometric series. Of this form here. 2/3, and here we have j plus k. Okay, using the laws of indices, we can split this to 2/3 to the power of j, 2/3 to the power of k. And here we take j 0 to infinity, 2/3 to the power of j, times the other infinite series, k equals 0, infinity, 2/3 to the power of k. So that's 1 over 1 minus 2/3 times 1 over 1 minus 2/3. That's 3. 3 over 2 times 3 over 2. Sorry, that's 2 here, so it's 3. I multiply this times 3 over 3 and this times 3 over 3. In the numerator I have 3 divided by 3, take away 2, times 3 divided by 3, take away 2, so it's 3 squared over 1 squared, and this gives me 9. So I have to split this double series into the product of the two series like this. Last example, finding Z transform of a discrete signal. Xn equals 2/3 to the power of n. The Z transform of Xn is the series from n equals 0 to infinity, xn times z to the power of minus n. So it's 2/3 to the power of n times 1 over z to the power of n. Let's write it this way. So this can be written as 2 over 3z to the power of n. And this can be written as 1 over 1 minus 2 over 3z. But here we need to find the radius of convergence, so 2 over 3z. this should be less than 1. 3z bigger than 2, so z should be bigger than 2/3. This is the region of convergence. So what this means, that you have a circle at the origin with a radius 2/3. So the value should be outside this circle. This is the region of convergence. Okay, this Z transform is used to transform the signal, to get the spectrum of the discrete signal. So n takes integers 1, 2, 3, etc. And what you find here is the spectrum. Z is a complex number, but we are not paying attention here. Now we also care about the calculating the series and the region of convergence here.